Hello learners! Have you ever flipped a schedule, turning days into time slots and time slots into days? Or rotated a table so that rows become columns and columns become rows? That's exactly what we do in mathematics when we transpose a matrix. The transpose of a matrix is formed by interchanging its rows and columns. Let's say we have a matrix A with order m by n, that means m rows and n columns. We denote A as A equals open square bracket A sub ij close square bracket of order m by n. Then the transpose of A, denoted A prime or a superscript T, is written as a transpose equals open square bracket A sub ji close square bracket of order n by m. Let's see a concrete example. Matrix A, first row 2, 3, 5. Second row 3, 2, 1. So A equals open square bracket 2, 3, 5, 3 to 1 close square bracket. Now to find A transpose, we flip rows into columns. A transpose equals first row 2, 3. Second row 3, 2. Now that we know how to transpose a matrix, let's explore its powerful properties. Double transpose. If you transpose a matrix twice, you get back the original. That is, A transpose transpose equals A scalar multiplication. The transpose of a scalar times A matrix is the same as the scalar times the transpose. That is, Ka transpose equals K times A transpose. Addition, transpose distributes over matrix addition. A plus B whole transpose equals A transpose plus B transpose. Product. This one's interesting. The transpose of a product of matrices reverses the order. So, A to B whole transpose equals B transpose times A transpose. These identities make it easier to simplify matrix expressions and solve matrix equations. Let's verify these properties using a real example. Let matrix A be first row 3, 3, 2. Second row 4, 2, 0. And matrix B be first row 2, 1, 2. Second row 1, 2, 4. Let's find A transpose. A transpose equals first row 3, 4. Second row 3, 2. Third row 2, 0. Now take the transpose again. Transpose of A transpose gives us back A. That's a double transpose property in action. Next, let's verify A plus B whole transpose equals A transpose plus B transpose. You can compute A plus B first, transpose it, and separately transpose A and B, then add them. They'll match. Also try this for a scalar. Say K equals 2 times B transpose should equal the transpose of 2 times B. These identities hold true and give us confidence in manipulating matrix expressions. Now let's verify the most interesting identity. Transpose of a product equals the product of transposes in reverse order. Let matrix A be open square bracket 2, 4, 5 close square bracket. Matrix B be first row 1, 3, 6. Second row 2, 4, 0. First compute A times B, you'll get a row matrix. Now transpose the result. Separately, find A transpose and B transpose. A transpose is 2, 4, 5. B transpose is first row 1, 2. Second row 3, 4. Third row 6, 0. Now multiply B transpose by A transpose and guess what? You get the same result. This identity is very useful when solving transpose equations, especially in systems of linear equations, machine learning, and vector analysis. Let's now dive into symmetric matrices. A matrix A is symmetric if its transpose is equal to itself. That is, A transpose equals A. This condition holds only for square matrices where the number of rows equals the number of columns. Mathematically, A sub ij must be equal to A sub ji for all I and j. Here's an example. Matrix A, first row 3, 2, 3. Second row 2, 1.5, 1. Third row 3, 1, 1. Transpose this matrix and you'll see it's exactly the same. That's what makes it symmetric. Symmetric matrices are widely used in quadratic forms, real-valued optimization, and in defining covariance matrices in statistics. Now, let's look at the mirror opposite skew-symmetric matrices. A matrix A is skew-symmetric if its transpose equals its negative. That is, A transpose equals negative A, which means A sub ji equals negative A sub ij for all I and j. Now here's an important observation. All diagonal elements in a skew-symmetric matrix must be 0. Why? Because A sub ii equals negative A sub ii. This leads to A sub ii equals 0, which means A sub ii equals 0. Example, matrix A, first row 0, 2, negative 3. Second row negative 2, 0, 4. Third row 3, negative 4, 0. Transpose it, you'll see that it matches the negative of A. These matrices are used in vector cross products, antisymmetric operations, and physics-based simulations like angular momentum. Alright learners, time to summarize our journey today. Transpose flips a matrix. Rows become columns, columns become rows. We write A transpose equals open square bracket A sub ji close square bracket. Key identities: transpose of transpose equals original matrix. Transpose of scalar times A equals scalar times A transpose. Transpose of A plus B equals A transpose plus B transpose. Transpose of product of equals B transpose times A transpose. A symmetric matrix is one where A transpose equals A. Only square matrices can be symmetric. A skew-symmetric matrix satisfies A transpose equals negative A and all diagonal elements are 0. These concepts are vital in data structures, matrix theory, system design, and physics. And that's the foundation of how we understand transpose, symmetric, and skew-symmetric matrices. I'll see you in the next lesson where we'll explore even deeper transformations using matrices. Take care and happy learning.